In this lecture, we're going to go over the basics of electromagnetic waves. So to begin, we first need to understand and get on the same basic ground with what is a wave. A wave is a propagating periodic motion. Propagate is a fancy way of saying it's something that moves through space or time. Periodic means it's got a repetition to it. And motion, again, goes back to the fact that it moves. Okay. Some definitions really quick that are true for all types of waves. The amplitude of a wave is related to its loudness, brightness. Oh, my thing here is not keeping up well. Okay, brightness, or its intensity. Okay, so if I think about a sound wave, the bigger the amplitude, the louder it would be. If I think about light, the bigger the amplitude, the brighter it would be, or the more intense it would seem. The wavelength is the distance it takes for it to repeat. Okay. Period is very similar to wavelength, but instead of distance, it's a measure of time for it to repeat. Okay. And frequency is the inverse of the period. So since the period is the amount of time it takes to repeat, the frequency would be a measurement of the number of repeats in a given amount of time. And I said it, but I'm going to write it here. T for period is the inverse of the frequency. So period is 1 over frequency. Okay. You can relate the speed of a wave to its wavelength and its frequency. And that relationship is that the wave speed, this is the speed, it's v for velocity usually, but we say wave speed, is the wavelength. That's the Greek letter lambda. Let me write that above here. This is wavelength multiplied by the frequency. So let's pick on a something that you probably don't know, but it will help illustrate this. Radio waves are a type of electromagnetic wave. They travel in vacuum at a speed of 3 times 10 to the 8th meters per second. In air, it's a little bit less, but we're talking not very much less. So we're going to go with the speed in vacuum, the wavelength, and then if we pick on a local radio station, maybe 97.5 megahertz, so that'd be 97.5 10 to the 6 hertz. I don't remember what they call that one at the moment. I just know it's one of the local radio frequencies. Then I can calculate the wavelength by taking 3 times 10 to the 8th meters per second and dividing by the frequency. And that gives me 3.07, the point kind of disappeared, meters. And now you may be looking at the units and going, huh? Okay, so the thing to remember is the unit of hertz is by definition 1 over seconds. So if I take meters per second and divide by 1 over seconds, that's the same as multiplying by seconds. Everything here cancels, and I'm left with just units of meters. So it really does all work out. Okay. There are 2 types of waves. This website does a good job of illustrating the 2 types of waves. So let me bring it up and show you. Okay. The 2 types of waves are longitudinal waves. So this illustrates longitudinal waves. And if you look, the wave is propagating to the right. But if you watch one of the red dots, they even have it labeled down here. If you look, it oscillates back and forth, left and right, left and right. And one important thing to notice is as the wave moves through the medium, the particles themselves don't move. They oscillate, but they don't propagate. So the wave propagates through the medium itself does not move. Okay. For a longitudinal wave, the direction of propagation and the direction of oscillation are parallel or antiparallel. So in this case, we're propagating to the right and we're oscillating to the left and to the right. Contrast that to a longitudinal wave, as shown here, where again the direction of propagation is to the right, but the direction of oscillation is now up and down. So for a transverse wave, the oscillation direction is perpendicular to the direction that the wave moves. Just because you can see it a little bit, I'll scroll down a little bit to water waves, and it turns out waves on waters are not transverse or longitudinal. They're a combination of the two, which is what this is trying to illustrate. Okay, so reiterating all of that really quick, a longitudinal wave is one where the propagation is, that's an is, parallel to the oscillation. And a transverse wave propagation is perpendicular to the oscillation. Okay, this video, I will post this particular PowerPoint up onto Sakai for you to look at, and you can go back and watch this video. It shows a teacher and a couple of students putting a cell phone into a bell jar. You can hear it ring and you can watch it ring when the bell jar has air in it. They then use a pump to remove the air out, call it again, and you can see it ring, but you can no longer hear it, which is illustrating the point down below here. Sound is a good example of a mechanical wave. Mechanical waves require mediums. All longitudinal waves are mechanical waves. Okay, so all longitudinal waves require mediums, which is why when you, in that video, when they pull the air out of the bell jar, you can see it ring, but you can't hear it. There's no medium left, so the sound wave can't propagate. Light, however, is an example of an electromagnetic wave. Electromagnetic waves can move through mediums, but they don't have to, and they are transverse. Now, you may ask, well, what is actually oscillating? Well, it turns out for an electromagnetic wave, the thing that is oscillating is the electric field and the magnetic fields. And regrettably, it is one of these situations where you're trying to display a three-dimensional phenomena on a two-dimensional screen. So what they're trying to show here is the red is the oscillation of the electromagnetic field. And if you think about that oscillating in the plane of the screen up and down, so the electric field is oscillating this way. The magnetic field is in blue, and it is also oscillating, but instead of oscillating into this weird diagonal, what they're trying to illustrate is that it is coming into and out of the page at you. And all the while that all this is happening, the wave is propagating in a third direction. So the direction of propagation is perpendicular to the electric field, which is perpendicular to the magnetic field, and all three things are perpendicular to each other. Okay. If you look at the electromagnetic spectrum, you can break it into regions, and that's what we're going to look at now. So first thing I'm going to do is I'm going to start at this end. I'm going to point out, hey, we're at the high frequency end, and because we're at the high frequency end, we are at the short wavelength end. If you think about visible light, this is the blue end of the spectrum. At the other end, you have long wavelengths and low frequencies. And this is all because of the relationship we learned a couple slides ago, that V equals lambda F. the speed of an electromagnetic wave in vacuum is fixed. It is 3 times 10 to the 8th meters per second. Because v is fixed, if the wavelength increases, the frequency has to decrease, and vice versa. Okay, so now starting at the short wavelength end of the spectrum, we begin with gamma rays, and then we can move into X-rays, and then UV, and then we hit visible light. Now, depending on who you talk to and the time of day and how they're feeling, you might get slightly different answers for what the range of visible light is. This particular schematic is saying the range of visible light goes from 7 times 10 to the 14th hertz to 4 times 10 to the 14th hertz. Those are the range in frequencies. In wavelength, it's pretty much reversed. So 7 times 10 to the 14th hertz would be about 400 nanometers. And 4 times 10 to the 14th hertz would correspond in wavelength to about 700 nanometers. Okay. So 400 to 700 nanometers, with the 700 end being the red end and 400 nanometers being the blue end, is basically the range of visible light. Moving past that, we move into the near infrared first, which is not labeled, and then fully into the infrared, followed by microwaves and radio waves. Okay, and notice that the example we used before was 10 to the 6 hertz, which is indeed down in the radio wave end of the electromagnetic spectrum. Okay. This is again a depiction of the electromagnetic spectrum. You can see they've broken it up a little bit differently. The high energy end is again to the left, the low energy end is again to the right. Down at the high energy end we have the UV range, and then they lump the visible all into this area right here. They then break up the infrared into near IR, short wave IR, mid wave IR, and long wave IR. Okay. And then after that is microwaves. And one thing you might notice is the units are changing a little bit. So the previous slide, I gave the range of visible light as 400 to 700 nanometers. This particular slide starts the near infrared at 0.75 micrometers, more often referred to as microns. Okay. Remember also I said the bound of the visible light spectrum varies on who you're talking to and time of day and all of that. Well, you're seeing some of that here because they're not starting the infrared until 0.75 microns, which is slightly different than where we ended it before. For reference, 0.75 micrometers is equivalent to 750 nanometers. Okay. Again, one more depiction of how these wavelength and frequency ranges fall out. Same idea, different scopes of how they're dividing things. Right? Okay, so all this is great. Now, let's apply this. And what we're going to think about is Landsat. When you did last week's assignment, you saw that there were 11 different files in one Landsat file download. And the reason for that is because, okay, well, there are 11 different bands. There were more files than that, but we'll go with that. Each of those bands covers a different portion of the electromagnetic spectrum. So if you go and look at them, so band 1 looks at coastal aerosol, and it is on the blue end, but the low blue end of the visible spectrum. Bands 2, 3, and 4 cover the visible spectrum, blue, green, and red, respectively. It then has a near infrared band covering that wavelength range, a shortwave IR, or 2 shortwave IR bands, a panchromatic band, and if you look at the panchromatic band, it covers most of, well, some of the blue range, all of the green, and some of the red. So it basically is a black and white of the entire scene almost. Then there's a band for looking at cirrus clouds and 2 bands for looking at thermal infrared radiation. Okay, this last column over here on resolution in meters, that's telling you how big the pixel is for each of these. We'll be covering that information in a later meeting. For this week, what I want you thinking about for the assignment is, depending on how you make your image, or depending on how you combine these bands. So if I do in ArcGIS band 4 on the red, band 3 on the green, band 2 on the blue, I should see a true color image of whatever the scene is you're looking at. But I don't have to do 432. I could do 431 or 765. And the question I have for you in this week's assignment is, what band combinations do what, or provide what information, was a good way of saying it. So if I want to look at a Landsat imagery, or a piece of Landsat imagery, and get an idea of how much of what's below me is urban or how much of it is agricultural, what do I look at? And that is this week's assignment.